Your phone pulls up contacts in milliseconds. Netflix recommends a movie instantly. Google searches 3.5 billion pages in a blink. How does any of this happen so fast? This isn't magic, it's smart engineering. If our devices had to search for everything, every app would grind to a halt, becoming completely unusable. We expect instant, but that instant is built on a fundamental secret, a core data structure. What we need to understand is how computers retrieve exactly what they need, not by searching, but by knowing where it is. Without this underlying mechanism, your digital world would crumble into a slow, frustrating mess. Today, we're breaking down the hash table, the invisible engine of instant access that powers nearly every fast application you use. Let's get to it. Imagine finding one specific person in a stadium filled with 80,000 cheering fans. Or locating a single book in a library with billions of titles, but without any systematic organization. That's the problem our computers face every second, retrieving specific pieces of information from a massive sea of data. Most people think computers just search really fast. But a typical search, like scanning a simple list, means checking every single item, one by one, until you find what you need. If you have a list of 1 million contacts on your phone, finding Zach could mean checking nearly 1 million names. This is called linear search, and it's agonizingly slow for large datasets, taking something known as time complexity. How do we get from finding a needle in a haystack to knowing exactly where the needle is? The solution is pure genius. Instead of searching, we use a trick called hashing. Think of it like a super smart, automated address book. You don't flip through every page to find Alice. You go directly to the S section, or the B section for Bob. The first letter is your key, and it tells you where to start looking. A hash table works on this same key-value principle. Every piece of data, every value, has a unique key associated with it. The magic happens when we transform that key into an exact physical address or index within the computer's memory. In 1953, Hans-Peter Lund at IBM introduced hashing for faster data retrieval, a concept that fundamentally changed how computers organize information. So, how does your phone turn Alice into a specific spot in its memory? It uses a hash function. This is a mathematical formula that takes any input, a name, a number, a web page URL, and computes a fixed-size output, a number. This output number is the hash value, and it directly corresponds to an index, a specific slot in a pre-allocated storage area, like a numbered drawer in a filing cabinet. For example, a simple hash function might take the letters in Alice, convert them to numbers, add them up, and then use the modulo operator to make sure the final number fits within the size of our storage array. A good hash function is designed to distribute these keys evenly across all available slots, minimizing clustering. Python's built-in hash function, for instance, uses a sophisticated variation of SIP-hash to quickly generate these unique memory addresses, making lookups nearly instantaneous. What if two different keys, like Alice Smith and Alicia Jones, get assigned the same memory address by our hash function? This is called a collision, and it's a critical challenge for hash tables. Collisions are inevitable, especially with finite memory slots, but smart strategies exist to handle them. Two primary strategies emerged in the 1960s to manage these clashes. The first is chaining. If two items hash to the same slot, we simply store them both in a small list or chain at that slot. The second is open addressing. If a slot is already occupied, the system looks for the next available empty slot nearby. Each method has trade-offs in terms of memory usage and speed, with chaining generally being more robust for higher data densities, often measured by load factor where above 0.7, collisions increase rapidly. This isn't just theoretical, you use hash tables daily without even realizing it. In programming, these structures go by names like dictionaries in Python, maps in JavaScript and Java, or hash maps. These are, almost universally, implemented using hash tables under the hood. When you create an object in JavaScript, or a dictionary in Python, you're building a hash table. Imagine how a programming language would store a list of users, each with a unique email address. Using a hash table, finding Alice at example.com becomes an instant operation. These structures offer an average time complexity for insertions, deletions, and lookups. That's constant time, meaning it doesn't get slower as the amount of data grows. This constant speed is why programming languages rely on them so heavily. Google Chrome's V8 engine, for instance, optimizes JavaScript objects using sophisticated hash table techniques to ensure your web browser feels incredibly snappy. Where else do these instant access machines make a difference? Everywhere. Consider databases. When you search for a customer by their ID, an index, often built on a hash table, allows the database to jump directly to that customer's record, speeding up queries by thousands of times. Or think about caching. Your web browser, or even giant data centers, store frequently accessed data in caches, which are essentially hash tables, allowing lightning-fast retrieval without re-downloading or reprocessing. Even your internet connection relies on them. The Domain Name System, or DNS, which translates human-readable website names like Google.com into numeric IP addresses, uses hash tables extensively for ultra-fast lookups. This allows your browser to instantly find servers across the globe. DNS resolution typically completes in between 20 to 120 milliseconds, a speed directly attributable to these efficient data structures. They are truly the unsung heroes making our digital world fast. So, what's the big takeaway? Hash tables are simple in concept but revolutionary in impact. They are the core secret behind virtually every application